Okay. A very good day to one and all, and a warm welcome to the 25th talk of the Inter-Society Weekly Webinar Series, jointly organized by IEEE Kerala Section, Institution of Engineers India Kerala State Centre, Computer Society of India Trivandrum Chapter, PMI Kerala Chapter, Internet Society of India Trivandrum Chapter, Vakam Maulavi Foundation Trust Trivandrum, and IEEE EMBS Kerala Chapter. And with us, we have our speaker, Dr. K Asraff, who is the Deputy Director of the Liquid Propulsion System Center, ISRO. And he will be taking us along with his webinar on the most astonishing number in the world. And so this is a really curious topic, I would say, and we are all waiting to hear from you. And so firstly, as we begin, I would like to welcome Ms. Bhagyashree VS for the welcome address. Can we have you, Bhagyashree?
Yes, Fita, am I audible?
Yes, yes.
Okay. Age is just a number. It doesn't matter who you are, where you come from, because the ability to triumph always begins with you. Good evening to one and all present here. I, Bhagyashree VS, welcome you all to the 25th webinar of Inter-Society Weekly Webinar Series. Topic for today's webinar is the most astonishing number in the world, the golden ratio, denoted by the Greek letter phi, which has an approximate numerical value of 1.618. Golden ratio, also known as golden section, golden mean, divine proportion, is often called the most beautiful number in the universe. The reason why phi is an extraordinary number is that it can be visualized almost everywhere, starting from geometry to the human body itself. The significance and amazing properties and applications of this amazing number would certainly be an interesting topic to be discussed about. With immense pleasure, let me welcome the speaker for today's webinar, Dr. K Asraff, Deputy Director of LPSC, Liquid Propulsion System Center, Research and Development Center, working under ISRO. Welcome, sir.
Thank you.
Next, I would like to welcome S. Radhakrishnan sir, Ashok Kumar sir, Harindralal sir, and all the eminent personalities who have gathered here for this session. Welcome, sirs. I also welcome Fita Fatima, the MC for today's session, and all other participants to this wonderful session. Once again, I welcome you all. Thank you.
Thank you, Bhagyashree. So next, I would like to welcome S. Radhakrishnan sir of the Institution of Engineers India to introduce our speaker. Can we have you, sir?
Thank you. Good evening and good morning to all the members and participants of the Inter-Society webinar across the globe. Let me first thank the organizers for giving me an opportunity to introduce our speaker, K Asraff, who is here with us to give a talk on the topic, the most astonishing number in the world. Let me also take this opportunity to thank Engineer A.G. Harindralal, Chairman, Inter-Society Activities Chairman, and his team for organizing this weekly webinar without fail. Being the past chairman of the Institution of Engineers India Kerala State Centre, I know how difficult it is to organize the weekly meetings without fail. We have been conducting for the last 20 years, it's Wednesday regular talk. Now let me go to the bounden duty of introducing Dr. K Asraff, Deputy Director, LPSC ISRO. He is a good orator, listener, and clarity in his thought. He is a dynamic, active, and a good teacher too. Why I say is, normally, as you know, structural engineering area is a very complex area. Many people unknowingly make mistakes while designing. What we get from Asraff is, while giving for analysis, when he finds out the mistakes, he suggests the problems and how to rectify it also. That's the advantage of going to Dr. Asraff for the analysis. Graduated from Kerala University, postgraduate from Anna University, and PhD from Abdul Kalam Technological University. He has presented 70 papers in both national and international conferences, out of which 5 papers got Best Paper Award. He is a recipient of ISRO Team Excellence Award in 2009. He has guided and also guiding many MTech and PhD scholars. Also, he secured copyright for 5 software developed by his team in ISRO. Today's topic, as you are knowing, is a very unique, the most astonishing number in the world. Actually, it is a number and its golden ratio. The most engineers were using in their day-to-day design calculations. Even though it was discovered by mathematicians of antiquity, the importance of this number can be seen in our daily life too. Let us hear more from the speaker, Dr. Asraff. Thank you.
Shall I start?
Sir, now it's over to you, sir. You can start. Yes.
Okay.
Now over to
Shall I start?
Yeah.
Okay. Good afternoon, good
Yes.
evening, and good night and good morning to people all over the world. At the outset, let me thank God Almighty for giving me this rare chance of addressing people all over the globe. I never thought in my wildest dreams that I would be addressing from a home the whole world. It is an honor, it's a privilege. I consider myself immensely lucky and fortunate. For this, I want to thank the office bearers of the Institution of Engineers India, Kerala State Center, especially President Engineer K Gopalakrishnan Nair sir and Secretary Ashok Kumar sir. And I wish to thank the office bearers of the IEEE Trivandrum chapter, especially Mr. Harinder Lal, who is the chairman of the Inter-Society Activities Committees Kerala Section. And a special thanks to Radhakrishnan sir, who has been my mentor at office. Mr. Radhakrishnan sir, as well as Ashok Kumar, we had worked together during the development phase of the GSL, the Mark III launch vehicle. It was a very wonderful experience. I really miss them out there in office. Radhakrishnan sir was a mentor and a well-wisher for me too. We had traveled together. We had spent time together many times. So without much ado, let me start my presentation. My presentation is structured like this. Initially, I will give a brief introduction to the world of numbers, followed by the most astonishing number and why is it astonishing, why people call it astonishing, and followed by closure. So as you all know, numbers can be classified into real numbers and complex numbers. Real numbers can be further classified into rational numbers as well as irrational numbers. And from this picture, you can see that the rational numbers are one which can be denoted or which can be expressed as a ratio of two numbers, let us say a by b, which are integers, and irrational numbers can never be expressed like such a fashion. So we can see pi is actually a irrational number, root 2, root 3, for everything is a irrational number, which we cannot express it precisely in terms of two numbers. For example, pi can approximately only be expressed as 22/7, but it can never be expressed accurately as 22/7. And we have natural numbers which start from 1, 2, 3, etc. And whole numbers we have 0 also added, and integers we have the negative numbers as well. And rational numbers can be, as it called, a by b, which can be negative as well as positive. The complex numbers are very useful in science and engineering, and it is expressed as a plus ib, where a and b are real numbers and I is -1. So let us now go to our number called the most astonishing number, denoted by phi or phi. It was discovered in the 5th century BC by Pythagoreans, and it is also called the golden ratio, and that is a number which is approximately equal to 1.618, and it is called one of the most irrational numbers, and it has inspired thinkers, philosophers, artists, sculptors of antiquity, starting from the Pythagoreans, Euclid, Da Vinci, and of late Dan Brown and Mario Livio, who is a very famous author of good books at Jerusalem, that is in Israel, and of late Roger Penrose, who is a professor at the University of Oxford. It has several other names such as divine proportion, divine section, golden number, golden ratio, and so forth. But I wish to call it God's own number, which we will see why is it so. Why is it astonishing? You would find the manifestations of this wonderful number starting from our human heart to all the way to mundane things like rabbits, Madhuri Dixit, our visiting cards, and the sunflower, etc. So what is golden ratio? Golden ratio, you can divide a line, let us say a line segment as two segments in a specific proportion such that the full length divided by the larger length is equal to the larger length to the smaller length. For example, a plus b divided by a. Here in this figure, I hope this figure is visible to you, and I am equally audible to you as well. A plus b by a equal to a by b. So this is called the golden ratio. And if you put A equal to 5 and then B equal to 1, then this ratio will be the golden ratio. And you can simply, by substituting, we can say it is 5 plus 1 divided by 5 equal to 5 divided by 1, and cross multiplying, you would get the famous quadratic equation 5 square minus 5 minus 1 equal to 0. And the positive root of this equation is 1 plus root 5 by 2, which is approximately equal to 1 plus 1.618. Negative root will be 1 minus root 5 by 2, which will be minus 0.65, which I am not going to discuss here. I'm going to discuss about 1.65. This number can be expressed to the 2000th decimal like this. It is a non-recurring, non-repeating decimal, fraction number. And as I told you, it is a very irrational number. And people have constructed or derived random number, generated random numbers out of this by choosing any series of numbers from anywhere in this expression. Now we will explore the manifestations of this golden ratio in various fields, various walks of life, such as mathematics, geometry, etc., etc. In the coming slides, I will be dealing with all that. So let us first explore the golden ratio maths itself first. Let us study the interesting properties, mathematical properties of this ratio. You can see that this golden ratio square is equal to 2.618. So the last digit, it will be the same. 1.618 square will be 2.618, and 1 by 1.618 will be 0.618 again to the last digit. And it can also be expressed as root of 1 plus root of 1 plus root of 1 plus, etc. And it can also be expressed as 1 plus 1 by 1 plus 1 by 1 plus and all that. And there is a small wonderful equation, 5 raised to n equal to 5 raised to n minus 1 plus 5 raised to n minus 2. And this equation can readily be checked with the first two equations on top. Now, simple tricks to get golden ratio in your calculator. Press 1 in your calculator, add 1, take reciprocal, add 1, take reciprocal, add 1, take reciprocal. If you continue this 9 times, you would get this ratio. Subsequently, you would get this ratio exactly. And similarly, press 1 in your calculator, add 1, take square root, add 1, take square root, add 1, take square root. Continue 9 times, you will get again this same ratio, and subsequently you will get this same number occurring. Now let us explore the presence of golden ratio in Fibonacci series. Fibonacci series is a very, very famous, popular series in mathematics. It starts with 1, and you add 1 to 0, and then you will get 1 again, and then 1 plus 1 you will get 2, 2 plus 1 you will get 3, 3 plus 2 you will get 5, 5 plus 3 you will get 8, 8 plus 5 you will get 13, 13 plus, and so on and so forth. This is a very interesting series. It was found by Leonardo Fibonacci in the 12th century. He was a very famous Italian mathematician from the city of Pisa, and he is considered as one of the most talented Western mathematicians of the Middle Ages. And he wrote a very popular book called Liber Abaci, in which he had expressed this series very nicely. And he was the one who introduced the Hindu-Arabic numeral system to the Western world, to the European world. So let us see a page from his famous book, Liber Abaci, where he has discussed the Fibonacci numbers. You can see this is an explorer view of the this particular section, and it is 1, 2, and all that. You can see how the series is derived. Now, how to see what's the importance of Fibonacci series and golden ratio? You take any two consecutive numbers and take the ratio of that, you would see that it will be equal to 1.618. So beyond the third digit or third series, it converges to the very fastly converges to the 1.618 number, which is the golden ratio. So if anything has got Fibonacci numbers in that, then it follows golden ratio as well. Now I've seen one more interesting thing, that instead of taking the Fibonacci numbers like 5, 8, and 13 and all that, I've taken 10 and 12, 10, 11, which are two random numbers, nearby numbers, and I've added to get 21, and then added 21 to 11, then to 32. Subsequently, it went like this. So they are all Fibonacci. They are not the Fibonacci numbers, but surprisingly, I found that the ratio of any two numbers is approaching 1.618 or golden ratio. So it's not necessary that the numbers have the Fibonacci numbers, any two numbers, but they have to be in the progression of Fibonacci. That is, you have to add two numbers to get third number, and so on and so forth. Now let us explore the golden ratio in geometry. I've discussed here, I've shown here three popular geometries. One is the square, one is the rectangle, and we have got a triangle and a circle. A triangle, a rectangle, let us say ABCD rectangle, the side AB to BC, if it is following the 1.6.8 ratio, it is called a golden rectangle. And if you have a triangle like this, and if I draw with the 72 degrees here and 36 degrees here, a very acute triangle, then and if you draw a angle bisector from here, then this will be AD divided by DC. This AD will be divided by DC will be equal to 1.618, and this is called a golden triangle. And similarly, a circle, if it is divided in the golden ratio proportion, then it is called a golden circle or golden angle. For example, this is 225, 222.5 divided by 137.5, it is 1.6. So this ratio is called the golden angle, or this circle can be divided as the proportion of golden ratio. Now there are certain interesting properties for the diagonals of a golden rectangle. This is a golden rectangle, and I can have a diagonal for this golden rectangle, a main diagonal for this golden rectangle. Then I take out the first square, the square I take out, then I get another golden rectangle. And if I take the one main diagonal for the second golden rectangle, so we have got one main diagonal here, another second main diagonal for the second triangle. Now comes the beauty. You take out the first rectangle or first square out of it, then you will get another golden rectangle. Take out the square out of that, you will get another golden rectangle. Take out the square, you will get another golden rectangle. Take out the square, you will get another golden rectangle. And all these rectangles will have two diagonals, like this main diagonal of this one. This one will be the diagonals for all these rectangles. So finally, you will reach this point, or the meeting point of these two diagonals, as the last number or last point. The same thing, I can as well draw a spiral connecting all these points like this, all these points can connect, and this spiral would be called a golden spiral or a logarithmic spiral. It will have an equation like this: r equal to a into e raised to b theta, where r is the radius from the center, and a and b are real numbers, and theta is the angle. And it is also called, this particular golden rectangle is a golden spiral or logarithmic spiral. It's also called a growth spiral or equiangular spiral, or spira mirabilis. Spira mirabilis meaning miraculous spiral. This equiangular spiral is defined by the angle. If you take any point and you draw a radial line and a tangent line, it will have an angle subtended. Then the same angle would be continuing all throughout this golden spiral. That is a property of this golden spiral. The angle subtends, the tangent and the radial will be the same with respect to the center. These things are very, very important, and this will recur in my presentation again. So I would invite the keen attention, rapt attention of the spectators, of the listeners to these aspects. Now the golden triangle, as I have discussed earlier, this triangle is called a golden triangle if you bisect this angle, and this will be the ratio of 5:1, and since this is 5:1, this will be 5, and this will be 5, this will be 5. This is called a golden triangle, and this also will be coming up in my presentations henceforth. So this is the golden triangle, and I can draw a golden a logarithmic spiral also like this. That is, I take out the angle bisector of this, and then I get a golden I get a golden triangle like this, and I take an angle bisector like this. I get a golden triangle like this, and this can be continued indefinitely. And if I join all these vertices, I get a golden spiral as well. Now this I have explained earlier. This is the golden angle, and it is 360 divided by 1.618 is 222.5, and 360 minus this 225.5 will 137.5. This angle also you will see manifestation of this angle. You would see a lot in the coming presentation, coming slides. Now this star-shaped geometry is called a pentagram, and if you draw like this, in my childhood I used to draw this with a pen without lifting the pen from the paper. You can straight away draw like this, and the beauty of this particular figure is that the ratio of any two sides would be in the golden ratio. For example, A, the total length divided by this length B will be 1.618, and B divided by C will be 1.618, C divided by D will be again 1.6. So this pentagram is an embodiment of this golden ratio. Now let us see pentagon. This is a pentagon, And if you draw all kinds of diagonals from this pentagon, you will get a pentagram. If you see closely, watch closely, you would see at the center an inverted pentagon. So again, we can draw diagonals from this, and you can still get another pentagram. So this pentagon, pentagram, pentagon, pentagram can go ever, forever, and all these things are related to golden ratio. Now let us see a concept, a beautiful concept called Platonic solids, which was proposed by Plato, a Greek philosopher and mathematician, very famous Greek philosopher and mathematician of the 4th century BC. He had represented the earth, fire, air, water, and universe as 5 Platonic solids, which have shown here. This is called tetrahedron, a cube, an octahedron, an icosahedron, and dodecahedron. Now, the importance of these two, the bottom two figures of solids is that they are based on golden ratio. The top 3 are not based on golden ratio, but the bottom 2 are based on golden ratio. That is the icosahedron and dodecahedron, which is water universe, are representing a golden ratio. Because if you see the mathematics behind this geometry, you can see it is, everybody would say, see the root 5 plus 1 by 2. Root 5 plus 1 by 2 is nothing but 1.618. So you can see here in this dodecahedron also a pentagon, which is again a pentagon, like pentagon thing, which is a solid related, very closely related to the golden ratio. Now let us explore the presence of golden ratio in art. You all know who is Leonardo da Vinci. I don't have to tell. He lived in the 15th century AD. He was Italian Renaissance artist, famous painter, sculptor, architect, engineer, designer, so on and so forth. And he had his paintings show very nicely. He portrays this golden ratio in his paintings. For example, he has painted the Madonna of the Rocks, and it's also called the Virgin of the Rocks painting. There are 2 versions of this painting. One is the Paris Louvre Museum, another is in the London Museum. So both are almost similar, except certain changes here and there. The beauty of this picture is that, or this painting is that, the painting is in the ratio of 1.6, very close to the golden ratio. And here also is 1.57, very close to the golden ratio numbers. Similarly, Da Vinci's very famous painting, Leda and the Swan, the hairdo of the lady is in logarithmic spirals, as you can see, logarithmic spirals. I have put a blown up picture of this. Am I audible to the audience? Can I get the feedback? Am I audible now?
Yes, sir. Yes, sir. You're audible.
Okay. If any problem is there, please let me know.
Yes,
I
sir.
won't be getting a feedback from you.
Yes, yes.
So the hairdo is in golden spirals, which is logarithmic spiral, which is a golden ratio related item. And in his famous painting Deluge, also he has drawn many number of such golden, such equiangular spirals or logarithmic spirals, which are again golden ratio related. Now I'll come to the painting of a very famous painter called Salvador Dali. Salvador Dali is a very famous Spanish painter and surrealistic painter. And his very famous work, which was done in 1955, called The Sacrament of the Last Supper, denotes, portrays Christ and his 12 apostles during the Last Supper. You can see that the first thing is that this painting is exactly in the ratio of 1.6, and a dodecahedron is painted engulfing table. Dodecahedron, as I told you, is a Platonic solid, and it denotes, according to Plato's philosophy, it denotes the universe. So this must be the universe, and this must be God. I think so. Now let us come to golden ratio in architecture. This is a very famous building in Greece. It's called Parthenon. It is the former temple of the goddess Athena in Greece. According to Greek mythology, Athena is a goddess, and this was the temple of Athena. It was constructed in the 500th century BC, 447 BC to be precise, and it is the most important surviving building of ancient classical Greek. And it was the facade of this building. You see, it is perfectly designed as per the golden ratio. And similarly, you might have heard about the pyramids of Egypt. And of all the pyramids of Egypt, there's a great pyramid of Khufu in Giza in Egypt. And if you see the half base width, it's a square pyramid, and there is an inclined height. So the slant height to the half base width is reported to be in the ratio of 1.62. So this building also is proportioned as per the golden ratio. Now comes the pentagram concept, which I've told you earlier. And you can draw complex patterns like this out of this, which are all based on the golden ratio. For example, if you take out this particular twin triangles, it is based on the golden ratio. As you know, this to this is golden ratio, so you can have a pattern like this, which is based on golden ratio. 5 is of course the golden ratio number. And similarly, this also a kite-like looking object can also be taken out like this, and which is also in golden ratio. And similarly, other triangles and quadrilaterals can be constructed out of this pentagram concept. And such patterns can be overlaid or laid together to form mosaic patterns, and they are called Penrose tilings. It is named after the famous mathematician and co-worker of Stephen Hawking, Professor Roger Penrose of Oxford University. Is a very great mathematician. He is probably one of the best mathematicians, living mathematicians in the world today. And he has made such patterns, and you can see here Professor Penrose standing on a room with the Penrose tilings itself. And these are some patterns in color, multicolor, the Penrose tiling patterns. And these are commonly used in mosques as decorative patterns. You can see a lot of patterns like this. And this is another pattern which is constructed out of it. The top pattern is not the white pattern is of course not anything related to golden ratio, but the inside pattern is actually multicolored golden triangles have been used for this particular good looking diamond shaped pattern. And there's another sculpture in Jerusalem which is also proportioned as per the Fibonacci series. We have one here, 2, 3, 5, and 8, which denotes the golden ratio. Now, of late, the Dubai frame. This Dubai frame was opened in January 2018. It's a very recent structure, and it separates the old Dubai from the new Dubai. And on northern side, we have the old new Dubai, and the southern side of this is this old Dubai. And it has won a very famous award for best architecture. It's called ThyssenKrupp Elevator Award for Architecture. This ratio, or this Dubai frame is proportioned as per the golden ratio. You can see the outer periphery has got 150 mm height, 150 meters height, and 93 meters wide, and it is perfectly as per the golden ratio. And it is located in the Zabil Park in Dubai, and it is considered one of the best architectural examples in the modern world. Now let us explore the golden ratio in nature. They say the golden ratio, almost all hurricanes, they are very close to the golden spiral or the logarithmic spiral. So this is an example of a hurricane in over Iceland, which approximately represents a logarithmic spiral. And there are other spiral natural things like natural spiral beaches. For example, some of the most famous logarithmic spiral beaches are that in Washington, Australia, and Venezuela. There is a specific reason for this formation of this spiral, logarithmic spiral beaches, because of wind pattern and the presence of vegetation and rock and sand and all that. It takes a natural shape like this, a curvilinear shape, which is very close to the logarithmic spiral concept. Now, I would also like to explain or try to find out the presence of golden spiral, logarithmic spiral in this broccoli. It's called Roman cauliflower, Romanesco broccoli. It's actually cauliflower. If you watch closely, it has got many buds. If you zoom more and more, you would find more and more golden spirals. If you see this, the whole thing has got several buds which are proportioned, which look like a golden spiral. So this is the top view or plan view. This is the original shape, and you can see several. A golden, a logarithmic spiral pattern here. And if you zoom further, every bud you would find this logarithmic spiral. And if you further zoom, everything has got a lot of smaller buds are there, which are again in golden ratio, the golden spirals. And if you zoom further, you would find again. This is the third zoom. You would find again golden spirals, and again this is fourth zoom. Again, you would find golden spirals. Inside also there are many number of golden spirals which are probably difficult to see with the naked eye. This is a fifth zoom level, and you can see many number of golden spirals in this Romanesco broccoli. So this is a very important, very astonishing finding. And then the second is the next is the golden ratio in pineapple. You can see this. I've got a pineapple over here. I hope I am visible. This pineapple is also visible to you. Is it visible, Pida ma'am?
Yes,
My
yes.
pineapple is visible. So, okay. This pineapple is a very well proportioned pineapple, and I have marked here with the red ink, with red marker pen, 3 spirals as depicted in this slide. I've got these spirals here exactly. Um, for example, I've just count here. It starts from here. There are 3 spirals, florets like this. One it goes like this, and another goes like this, and another goes in the other direction like this. And if you count these things, I will count the vertical, almost vertical one. So if I count, I would find 1, 2, 3, 4, 5, 6, 7, 8, exactly 8 florets here in this direction, vertical direction, which is what is shown here in the middle one. There are exactly 8 spirals, which is almost vertical, but it's not perfectly vertical. Then there is another thing going like this, another spiral going like this. I've marked using red, and I can count it like this. It starts from here at 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So there are 13 florets here in this, exactly 13 numbers, and starts from the base and goes all the way to the top, and beyond this there's nothing. So this is the 13th spiral, and I have seen here there is another spiral over here. It starts from here and goes all the way here. I can count it for you. This is 1, and this is 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, and 21. So there are 21 spirals here. Whatever I have shown is a shorter, in the picture, it's a shorter pineapple which has got 5, 8, and 13. But whatever I have here is a longer pineapple which has got 8, 13, and 21. So it is a very, very wonderful. It exactly matches. Even I am very stunned, and rather I would say charged, excited by this amazing finding. I often does this example, and this time it has come very, very precise, very, very precise, and I am really excited about this. So I'll go to the next slide. In pine cones, also in golden ratio, you can see in pine cones there are spiral patterns here in the clockwise direction as well as anti-clockwise direction. And you can see here 13 spirals in the pine cone and 8 spirals in the anti-clockwise direction as well. So these are Fibonacci numbers, and they represent golden ratio as well. Similarly, in sunflower also, you can see in the central floret, you can have pattern. You can see patterns. The seeds are arranged in patterns like this. For example, there are many number of spirals in the clockwise direction and many number of spirals in the anti-clockwise direction. They are not the same number. They are not the same. They tend to be the Fibonacci numbers 34 and 55. And these are not actually observations alone. There are references. For example, there's a book called Algorithmic Beauty of Plants, Algorithmic Beauty of Plants, in which the authors, it is written by 2 authors, they have done mathematical simulation of these floret patterns using very different angles. And they have found that it exactly matches with 137.5. I'm not able to express that more. Neither would you find it interesting if I talk more about the algorithm they have used. But I have seen one thing. If they change the algorithm, the angle 137.5 degrees to 137.3 degrees, you won't get this pattern. Similarly, 137.7 degrees also, either 2 degrees, 0.2 degrees this side, that side, you won't get the same pattern. So it is a very strange coincidence that this you would be able to replicate this pattern using 137.5 degrees in the algorithmic calculations, which is nothing but the golden ratio number. Now we will see the pattern and the golden ratio plants as well. I have myself experienced this. For example, this is a video which I've shot at Munnar. This is a sunflower plant, and you can see the leaves are arranged in the golden ratio. For example, the first leaf would sprout out like this, and then the next one would be rotated by 137.5 degree and then going up. So you can see one angle 137 point, another 137 point, and all that. I'll just show you once again. Probably the previous slide will show you the exact pattern. For example, the first leaf would be here, The next one would be 137.5 degrees. The third one would be 135. Go up, and then another 135. So like that, it goes 1, 2, 3, 4, and all that. So the same thing is shown. I've seen. It's not that every leaf would follow this, but most of the leaves I've seen follow this particular 137.5 degrees. So it's a very amazing and astounding finding, which I've myself experienced. And when I explored more, I read that it gives this particular pattern gives the best exposure to sunlight and best space to grow. That's why it's called a growth. It is something related to biological growth as well. So now let us see the next item, which is the acacia leaves. Acacia tree. Here also I have myself experienced the angle, the 137.5 degree angle. This is acacia tree leaves, which is very commonly seen in Kerala and South India. And it is part of the social forestry. A lot of trees are grown by the Kerala government all over here. And you can see the leaves this is a stem, and the leaves are sprouting out like this. And here also I've seen in many locations the 137.5 degree golden ratio angle. So this I've collected myself from my neighborhood, and here also the leaves are arranged in this pattern of 137.5 degrees with each. So this is another, even the same angle you would find in flowers as well. For example, the petals of the flowers, if first the petal number 1 would be here, the petal number 2 would be here, and 3 would be here, and 4 would be here. Everything would be separated out in 137.5 degree angle, which is the golden ratio angle of 360 degree. And you would also find another stunning finding that the Fibonacci numbers you would find in flowers as well. For example, you would find most commonly you would find single petal flowers like water lily, and you have two petal flowers, 3 petal, 5 petal. I have seen 5 petals maximum. So when I went around my colony, housing colony, and tried to collect flowers, I found that all the flowers which I could have collected were 5 petaled. Similarly, you can have more petals like this, and which are all in Fibonacci numbers. So we can find that here. So lily, 21 petals, and so on and so forth. Now comes the bifurcation angle in leaves. Bifurcation angle is the angle which it takes when it bifurcates from main stem. Either the stem can bifurcate, or the leaves can bifurcate, or the part of leaves can also bifurcate. So bifurcation angle for Korean arbor vitae is found to be 34.44 degrees, which is nothing but 1 minus 0.618 to 90. So this is the if you take a 90 degree angle, and this would be the golden ratio of 90 degree angle, 1 minus 0.68. And you would also find that the other part, that is 55 and all that, that will also be another golden ratio number. So in some of the plants, some of the leaves, you would find this 34.4, and in some others you would find the other part of the golden ratio, for example 55.6 degree. So this was reported by in this journal, Progress in Natural Science, Modeling Golden Section Plants. Very beautifully they have expressed the bifurcation angle in Korean arbor vitae, as well as cypress leaves. Here also you can see this angle, the main stem, main direction, the angle would be 34.4 degrees. And similarly in bamboo branches also you would find branches, it takes 34.4 degrees. And similarly in poplar trees also you would find this angle would always be this stems, these branches would be always 34.4 degrees. However, in peach trees you would find this angle is 55.6, which is nothing but the 0.618 times 90 degrees, which is seen here. So in plants, most of the plants and leaves and trees, you find the same golden ratio present. Okay. Now let me discuss the golden ratio in animal world. For example, you have several molluscus. This is actually a snail which has got a shell, which is also called a molluscus. There is a very special molluscus called the Nautilus. The full name is Nautilus pompilius. This is a photograph of the Nautilus, and it's a cut cross section of the Nautilus. And this is an X-ray view of the Nautilus. And if you this geometry of this is very, very closely similar to the logarithmic spiral. So that's why it's called. And this particular shape will permit or will promote life or growth of the creature inside. So that's why it's called a growth spiral, because as it progressively grows, this shape also takes out more space for it to grow out. So that's why it's called a growth spiral. Now comes the Fibonacci rabbits. The Fibonacci series, what Fibonacci himself has proposed was that for the fast breeding of rabbits, it is found that rabbits breed at a very fast rate. And if you hypothetically keep one pair of rabbits in a yard and don't allow anybody to go out, or neither any rabbit to go out or any rabbit to come in, and have a closed environment to live. And if you put one pair of rabbits, one female and one male, and allow it to breed, then within a month, let us say if you're starting in December, up to January, it will grow, they'll become a full adult. And then the next month, they will give birth to another pair, and another, it's actually, it is called a twin, a male and a female again. So this is a red colored female and male. And so if you see, the number would have become 2 pairs or the 4. And the next month, what will happen is this will be there. The original black pair would be there, and the black pair would give birth to another blue pair. And this red pair will be there. They will achieve adulthood the next month. So the next month, we will have 3 pairs. And the next month, what will happen is this old red pair will be there, the black pair would be there, the blue pair would be there. And the black pair would have given birth to another brown pair. And this would have, the red pair would have given to a green pair, so on and so forth. So every month, the original pair would be there, and there will be an additional pair, and the additional pair would become adult, and then they will start becoming breeding again and again. So this is based on a theoretical construction or theoretical concept or theoretical assumption that there are no deaths in this family, and there are no external disturbances. So the growth is undisturbed. So if you see the total number of rabbits at any point of time inside this enclosure, inside this yard, it would be in the Fibonacci series or Fibonacci number. That's how Bernardo Fibonacci had proposed the concept of Fibonacci numbers. So you can see here, this is one pair. The number of pairs will be 1. This will be again 1. This will be 2. This will be 3. This will be 5. This will be 8, and so on and so forth. So these are called Fibonacci numbers, Fibonacci rabbits. And the series is called Fibonacci series. Similarly, the family tree of honeybees, you have seen many honeybees, honey beehives and all that. So there is a difference between the honeybee and the male honeybee and the female honeybee. Male honeybee are born out of unfertilized eggs. For example, this is a female honeybee, and the red denotes a male honeybee. So the red one is a male honeybee, and the small one, the plus mark, is actually female honeybee. And female honeybees are born out of fertilized eggs. So they are theoretically they are called, they have 2 parents. One mother and one father. So the father is here, the mother is here. But a male honeybee will have only a mother. So this is the difference between a male honeybee and a female honeybee. And if you explore the number of the genealogy of a honeybee, you can, if there is a male honeybee, it has got a mother, and mother has got a father and a mother, and this father has got a mother has got father and mother. So it goes like this. So if you take the genealogy of any honeybee, and if you trace the genealogy, you would find that the number of honeybees are always in the Fibonacci series. For example, this is only the first honeybee, that's the male one. This is female one, and then you have the 2 parents, and 2, 3, 5, 8, 13, 21. So the family tree of a female honeybee also would be, of a male honeybee would also be according to the Fibonacci series. And similarly, if you take the genealogy of male honeybees and generations, you got the number of males, number of females, and the total number of honeybees. So everything would be in the Fibonacci series, and everything would be as per golden ratio. So if you take the total number also, so at any point of time, if you take a honeybee beehive and start counting the number of males and male and female honeybees, it will always be in the proportion, the golden ratio proportion. The astounding thing is that both the male honeybees also following this ratio, female honeybees also following this ratio. The total also is following the same ratio. Now, the next topic is, or next interesting fact is the flight path of falcons. Among falcons, there is a special falcon called peregrine falcon. It's a very fast bird, and it preys on fish, on aquatic life. And when it takes a flight path, it travels at very high velocities, and when it tries to pick up the fish from a pond, or let us say a lake, it doesn't go straight to the fish and take it, because it has the eyes are located on either side of its head. So what it does is it always looks at the prey and tries to locate it, whether it is moving or not. Suppose, I mean, assuming that the prey is a fixed one, there is a fish is at a fixed location, then what it does is it keeps an eye on it always and takes a very fast path, which is almost equal to the logarithmic spiral. And the logarithmic spiral, as I told you earlier, it is having an it is also called equiangular spiral. So with respect to the radial line, with respect to center, the radial line and the tangent will be having the same angle all throughout. So it fixes the prey and then takes a very fast path down below and then takes the prey out and goes. So this is the flight path and photograph of a peregrine falcon. And this is very well documented in this particular journal paper, Journal of Experimental Biology, curved flight paths and sideways vision in peregrine falcons. So this is a very important, very startling finding for me. Now, some golden ratio human body. So as popularly discussed, human body also shows this ratio. For example, if you take your height, total height, and the height from the navel to the base, it will be in the golden ratio, and your bones, your thigh bones will be in the golden ratio, your arms will be in the golden ratio, fingers will be in the golden ratio. So if you take this distance and this distance, total to this one will be golden ratio, and this to this will be in golden ratio. This is for a well-proportioned human body, and one of my friends has done this study, and he found that it is very, very closely following this golden ratio. His body dimensions very closely follow this golden ratio dimension. For example, the bones also follow this golden ratio, but not for everybody, but for most of the people it matches well, very well. Now, recent paper, this is a recent paper published in 2014. What the authors have done is they have studied the systolic and diastolic pressure, the blood pressure in a human body, and tried to correlate whether it is as per golden ratio. So as you all know, there is a ratio called, there's pressure called systolic pressure, which is the maximum pressure or the high pressure, and the low pressure, that is the diastolic pressure, the lowest pressure. So generally we say 120 bar 80 or 140 bar 80 and all that. So this is the systolic pressure, diastolic pressure. This is the pressure at rest, and this is the pressure at full pumping condition. So the ratio, these pressures actually vary when we are in the daytime, and the nighttime also it varies. So when the researchers have done over a population, they have done studies of this ratio of diastolic, systolic, diastolic ratio, and they have found that it is in this ratio 131 bar 80. And there is a scatter also. They have taken the mean. Mean is actually 131. The systolic pressure and diastolic pressure is 80, and this is very closely following the golden ratio. And I've seen another paper which talks about the heartbeat rates also, but I've not put that here. But definitely the golden ratio you can see in human blood pressure as well during rest, during day and night time. And in golden ratio universe, you would find the Milky Way galaxy itself as a spiral galaxy, as a logarithmic spiral galaxy, and Pinwheel galaxy, which is also another galaxy. All these galaxies are very close to, not exactly, but very close to the logarithmic spiral, which is the equiangular spiral. Now, this is golden ratio structural engineering. This is what I've done my own contribution. I, being a structural engineer, I've done some studies on the influence of golden ratio on domes. You can see several domes. For example, most of the domes you can see in Italy, and this is in Jerusalem. Sorry, this is in Israel. And in antiquity, we had brittle materials only as construction materials, as civil engineering construction materials. And people used to have bricks and bricks mortar, and then ashlar mason, rubble masonry for construction of domes. But with the advent of reinforced concrete, we have tension also possible. So here, what is seen is, if you have a spherical dome, and if it is under self weight, it is seen that the hoop stresses will be compression to some extent, and then tension to some extent. So if the shell is deep enough, then there will be a point beyond which it will be in tension, but the upper portions will be in compression. So if you have a brittle material only as your construction material, then it is better to curtail or stop your construction with this dome only. But if you have a brittle ductile material like reinforced concrete, where you can take tension as well. You can plan a deeper shell like this. So the expression for hoop stress is this: PR by T into cos square phi cos square theta minus cos theta minus 1 divided by 1 plus cos theta. This is a very famous equation because you can see phi square minus phi minus 1. It is the golden ratio equation. And if you solve this, you would find theta equal 51.5 degrees. So up to 51.5 degrees with respect to vertical, it will be in compression, and beyond this it will be tension. And if you use a ductile material, there will not be any problem. But if you are using a brittle material, you are bound to have vertical cracks like this. So this was known to people of antiquity when they started designing these dome structures. So they had initially curtailed or stopped the construction up to here, design up to here, but subsequently with the development of reinforced concrete domes, we could go for a deeper depth. So this I've done in ANSYS fundamental analysis code, a spherical dome at model, and then applied the self-weight as the loading, and then see how the hoop stresses contours are looking like. So you can see that the top portions are all in compression, the negative things are all in compression, but the bottom portions are all in tension. So I had to put the tension and compression dividing line here. All the cyan color portions are in compression, and all the red color portions are tension. So this is actually the golden angle. This angle is actually as per the golden ratio, and so this is the manifestation of the golden ratio in structural engineering as well. Now comes a very interesting topic: golden ratio as a measure of beauty. Golden ratio has been used as a measure of human beauty, of the facial beauty of persons. This is a published paper. This is a paper from Science Direct, that is International Journal of Human Computer Studies, where the authors have studied the face proportions, both lengthwise and breadthwise also they studied. But I've put here the lengthwise studies or the heightwise studies. You can see several ratios for face. For example, from the tip of the forehead, the topmost portion of the forehead to chin, if it is denoted as 1, and 2. The mid of the eyes to the chin is the dimension number 2, and 4 will be from the eyes to the forehead, and so on and so forth. There are 8 dimensions given here, and they are explained here. And if you see, if you can have the ratios as well. For example, 2:4, 3:5, 6:7, and all that. And take the mean ratio. The mean ratio has to be for a beautiful face. It is told that it will be very near to the golden ratio. For example, let us take the ratio 2:4. 2:4 is from the eyes to the tip of the chin, and eyes to the tip of the forehead. So this ratio is very close to the golden ratio 1.6. We say that the face is a beautiful face. And this is one of the most beautiful faces in the Indian cinema. Madhuri Dixit. The ratio is 1.675. I have myself measured this photograph all these dimensions 1, 2, 3, and all that, and calculated, and I found that the mean ratio is 1.675, which is very, very close to the golden ratio. Now comes another interesting, other startling topic: golden ratio smile design. This is very commonly used by dentists. The dentist, actually, this is based on my studies are based on this particular paper: maxillary anterior tooth width proportion, a literature review. In this, they have studied 2-3 proportions for smile design. Smile design means the way the basis on which a smile or the tooth setting is supposedly the best one. There should be a reference. There should be a reference, and dentists base their reference on this particular proportion. There are 2-3 proportions shown in literature. It's called Preston ratio as well as golden ratio. Golden ratio is actually, you see the front dimensions. This is 1.62 to 1 to 0.62. All these ratios are as per golden ratio. There's golden ratio numbers. So if you set at the front of the frontal teeth according to this setting, then it is supposedly the best tooth setting, and the smile is supposedly the best smile. So this is the ratio, or this is the reference with which dentists proceed and set the teeth of the patients. Now, this is the last topic in my presentation: golden ratio in everyday life. Everyday life, you would see around us golden ratio. For example, they say golden ratio in Apple logo can be made out of Fibonacci circles. For example, you can have a circle of 13 radius, 8 radius, 5, 3, 2, and 1, and start constructing this Apple logo. And similarly, all the credit cards, I have myself measured all the credit cards, debit card, plastic money, everything is in this ratio 1.6. Similarly, the National Geographic emblem the inner dimensions are as per golden ratio, and the legal paper size is also as per golden ratio. And almost all business cards called visiting cards are all also the same golden ratio. Now I've completed before my 1 hour mark. To summarize, golden ratio called phi or phi is a lesser known cousin of pi, the ubiquitous, omnipresent mathematical constant pi. But nevertheless, it is a very magical number, and its manifestations are quite astounding. And new research, as I've shown you, 2014 papers, new research reveals more and more manifestations of this number. This very, very strange and a very enigmatic number in different walks of our life. And I've presented here today. I've presented here whatever I have studied, I have understood. There are other areas, topics, as for example, Beethoven's symphony. They say there is a golden ratio, but there are several false claims also. For example, in Taj Mahal, you would find golden ratio. In that you will find gold. But I, whatever I could verify, whatever I could understand, assimilate, and express, only I've added here. For example, there is for Stradivarius violins, which are supposedly very, very costly violins. They are positioned the F holes of violins according to this ratio, but I have not been able to understand nor study the number and verify whether it is true or not. To summarize, this number denotes beauty and perfection, and I strongly feel that this must be the signature of Almighty. Thank you. These are my references. I've based this studies has stemmed out of the famous book by Da Vinci, Dan Brown, Da Vinci Code. This is an illustrated Da Vinci Code. My wife rather prompted me to study this wonderful number. She was the first to read this book, and then she told, you should definitely read this. It will be very, very interesting for you. Apart from the religious angle and other angles of this book is a really wonderful one, and it introduced me to this vast world of golden ratio. And since then, since 2004, I've been doing studies in this wonderful number. And I've also referred to the famous book by Mario Livio, The Golden Ratio, the story of pi, the world's most astonishing number. And I've put the title of my presentation as same thing, the world's most astonishing number. So thank you all. I hope you have enjoyed it. Hope I did not trouble you with much mathematics as well. Thank you.
So thank you so much, sir. And I would say, as a student, I would like to say that we don't realize things like this around us, and it is really beautiful hearing from you, sir. And so I think, can we move on to a question and answer session now?
Sure, please go ahead, ma'am.
I'm a student, sir.
Okay.
Yeah. So we have a question from Thaila Ananthakrishnan. So she asks, can the golden ratio be explained in temple architecture? Like, she's referring to the temples of Khajuraho.
I've never studied that. We might need a careful study of the photographs and pictures, and the plans are available. We can have a study. But definitely, one thing I would like to tell you, temple architecture I have not studied, but Renaissance architecture, especially those in Italy and Europe, they are mostly out of this. But I will not be able to confirm unless I study that. But one thing I've seen, if you take a ground plot, I mean a plot for house construction, it would be better to have a rectangular plot than a square plot for obvious reasons. Civil engineers always prefer rectangular plots, and rectangular plots, the best plot is actually a golden ratio plot, because you can position the house in the middle. There will be front portions. There will be a portion left for front parking cars and all that, and there will be backyard also for nursery and things like that. So, okay, I have to answer your question, ma'am. I would not be able to confirm that without looking at it.
Okay, sir. Thank you, sir. So next is a question from Venkateshan Narayanan. And the Dubai frame has been apparently designed to the golden ratio. Was there a good structural or architectural reason for such a choice?
There are studies. For example, there is a journal paper published in Journal of Psychology, I think, where people have studied, they were given different shapes, for example, squares, deep rectangles, narrow rectangles, golden rectangles, and so on, so forth on a population, and they were asked to choose the best appealing, aesthetically appealing rectangle. And most people have chosen, it seems, the golden ratio rectangle. So golden ratio rectangle is supposedly a very pleasing, aesthetically pleasing shape rather than a square. You would yourself find it. You draw a square, you draw a rectangle, you draw a narrow, very narrow rectangle. You would find that the golden ratio rectangle actually has got an aesthetic appeal, a measure of beauty. Beauty cannot be measured in numbers, it can only be shown in proportions. So this psychologically, people have studied that and then reported that this is the aesthetically most appealing shape, square, rectangular shape.
Okay, sir. So there's a question from Ravindranath, and he's asking, he finds that everything in nature shows and follows a typical pattern. So he's asking whether everything is mathematical. So is there any further thing above that, or is it mathematical, just basic mathematics?
It's a tough question. Everything I would say is ordained, divinely ordained. God can be seen in mathematics. There was a book by calculus on calculus by famous author. He says that if you study calculus, you would be able to visualize God, because using calculus you can define many of the natural phenomenon in science and engineering. Natural phenomena use calculus and differential equations. So everything must be mathematical, I feel. But it occurs so random, so chaotic. So we apparently there may not be any reason or rhyme in the naturally occurring processes. But if you look at it, apparently there must be some underlying mathematics as well. World is chaotic sometimes, but in chaos itself there is mathematics.
Okay, sir. Thank you, sir. Yes, hopefully the answer is okay with the person who asked the question. So next is a question from Dr. N.N. Panikar. So he asked, does it contribute to efficiency and conservation in nature?
This is actually related to biology. The shape is actually very closely related to biology and beauty. So definitely it must be efficiency oriented. For example, as I told you, the golden spiral, that is the logarithmic spiral, is also called a growth spiral. So it must be efficiency oriented as well as life oriented, I would say. So if you see the plant growth, the leaves are ordered in such a fashion that it gets optimum sunlight. So it must be rather than efficiency, I would say it must be life oriented or growth oriented.
Okay, sir. Yes. And so in the chat box, there are many appreciations that you can get because this was a beautiful presentation, sir. And it is really interesting to know such new things. And so we are about to come to an end of today's session. And now as we come to an end, I would like to welcome Ashok Kumar, sir, Secretary of Institution of Engineers, India, to give away the vote of thanks. Can we have you, sir?
Yeah, hello. Am I audible?
Okay.
Yeah, you're audible.
Yes. Okay. Hello,
Yes, sir,
everyone.
yes, sir,
Good
you're
afternoon
audible.
from Trivandrum. I'm Ashok Kumar. As usual, as Dr. Asraff has made all of us wonder how beautiful the area of mathematics is. Though actually in our school days, we hated the subject, at least I hated the subject of history and this kind of initial mathematics things. At least when I'm inducted into the area of applied mathematics only, it started to be somewhat interesting to me. But then I never thought that there is so much mathematics even in nature and even in everything. But today I wonder whether I will be able to enjoy the beauty of a flower today, I will be always looking for the Fibonacci series or a logarithmic spiral or the golden triangle, etc., etc. Always I will remember Ashraf. I think you can have one more PhD in the mathematic applications in nature or something like that. All of us were spellbound all along your presentation, Dr. Ashraf. And I think as I seen in the chat boxes, I think this is one of the most interesting lectures, that too in mathematics, I would say, and that too by a structural engineer. Again. So all fine. We are all spellbound. Thank you very much for giving this a wonderful evening to all of us. Thank you very much, Dr. Ashraf.
Thank you.
Thank you, sir.
Yeah, I also thank all the volunteers who have been part of this conduction of this seminar. Fatima, Bhagyashree, Esther Thakshan, and all. And once again, I thank all of them. Then the office bearers of all the participating organizations, without whose supports this seminar series could not have been conducted in such a successful manner without any break from where we started. And then to all participants, thank each one of you for your participation all along through this series and through your very enjoyable questions and very correct questions and participation. Thank you one and all. Have a nice day.
Thank you, sir.
Thank you.
Sir, Ashraf sir, can we have one more question? So there's one more question that we have in the chat box.
Yeah, no problem. I'm always ready.
Okay. So why? So there's a question from Hafiz Hazan. So why does anything in the golden proportion feel appealing to us? Are we pre-programmed?
It's a very tough question. Are we pre-programmed? I don't know. Something. These are all related to psychology. It might be that we are pre-programmed. We look at things. Most of us say that ugly face is ugly face, and most of us say that if good face is there, we say it's a good face. So it must be that we must be pre-programmed, preordained, I would say, by Almighty. To look at, I've read somewhere that a thing of beauty is a joy forever. So we must be pre-programmed. But I would also like to say one more famous saying: beauty is in the eye of the beholder. Something which is beautiful for me may not be that beautiful for others. So it's a tough question to answer, Hafiz.
Yes, sir. Thank you so much, sir. And as I told, this was a beautiful presentation, sir. And I would like to inform everyone about our next session. Sir, can we have our next? Okay. So next is the Inter-Society Weekly Webinar Series Talk number 26, and it is about synergistic self-management, and it is by Dr. Anand Panikar. He's an international expert in Gandhian philosophy and practice and in ocean engineering. And it is on 7th of October, which is next Wednesday from 6 to 7 p.m. Hope all of you will be attending that session as well. And once again, Ashraf sir, beautiful session. And I request everyone to kindly fill the feedback forms also, which was there along with the invitations. So once again,
may I ask one point, ma'am?
Yes.
How many attended
Yes.
the talk?
So we have around 80 we had in this session, and we were going live. So in the live session, we had more participants too. We had a huge number of participants.
Okay, thank you.
So.
Thank you.
Yeah, and the chat box is filling with comments, sir. It's beautiful. And so that's all with the session. Thank you so much, everyone. Thank you to all the attendees of today's event. And once again, thank you to sir. Thank you so much, sir. Thank you all the speakers in today's evening. Thank you so much.
Fida Fatima, shall I add one comment about your comparing? It was wonderful. Your English was flawless, and without the typical Malayalam accent, it was really good listening to you, ma'am. Thank you.
Thank you so